In this section, we'll look at how to decode a Lempel-Welch coded text. Question?
Because you might miss, does that mean that the encoding process can miss sometimes the most efficient way of encoding if it misses some of the really long phrases which get repeated?
Yeah, okay, so the question was, is it possible that this encoding method misses the longest phrases or the best way to compress? I mean, taking your question in the most general sense, it definitely will sometimes miss the best way to compress. Remember this fractal picture where we said the ultimate way of compressing is write a program that produces the image. And this is a problem that's not just expensive to compute, it's utterly impossible to compute with a computer at all. So in that sense, definitely it will miss things. There are ways, there are things that are good about this. We won't talk about this in the lecture, but since you asked, it's kind of an excuse for me to digress a bit. The Lempel-Welch methods have some properties that are similar to Huffman codes. So they achieve something like Huffman, but in a stronger sense. They can achieve something like kth order empirical entropy. So this is like the entropy we've seen, but you take into account what was before the symbol as well. And that kind of reflects this repetitions. In another way, I think people are still, this is still active research. Find something that is like entropy. So you just take the text and you compute some number from the text, and that expresses the compressibility of that text. Again, the ultimate thing would be Kolmogorov complexity, which is out of the question. But some somewhat sensible way of doing this that reflects the type of repetitions you can pick up with schemes like that. There's still no definitive answer to that. It seems to be tough to capture this exactly. If you ask more humbly, there are specific strings where you can show that Lempel-Welch doesn't do great, and a slight twist of the method does much better. So in that sense, also yes. Maybe that was the question you had in mind, because if you look at some specific examples, you sometimes it springs jumps at you that you can do slightly better, but it's tougher to make this into a general method then. Yeah, so that's is a good part of the decoding chapter, so I don't want to cut this out. Let's leave this in. It's a good question. Before we come to a little more of discussion how well this works, let's see that we can actually decode what we produced with Lempel-Welch. As always, decoding is the opposite of encoding, so kind of we just replay what the encoder has done. So the decoder will have to play the same game of growing the dictionary whenever you decoded one phrase. So for the decoder, this looks as follows. You decode a substring y of the text, of the source text, by means of finding it in the dictionary. And after you decoded y, you have to add from the previous phrase a new code word to the dictionary, right? So that's in the picture, this y is the thing you encode now, or you decode now. And it points to some earlier occurrence of this substring. So that's one phrase in your dictionary. And after you've decoded y, you still have to do what the encoder would have done, which means add x and then this new symbol c to the dictionary. That's the same steps that the encoder would have done. It's just we have to delay this adding things to the dictionary a bit, because we have to wait to see what y is before we can add this new character to the dictionary. Okay. If we've decoded y, then the first character is this c. I think that's so far clear from the picture. Let's see how this works on an example first, and then code will follow. And pay close attention. Okay, so here's a sequence of the code words for phrases in the dictionary. We start the dictionary in the same way as before. So we initialize it with all the characters in the alphabet. So here again, the ASCII characters. This will be a different example, yeah. But the same initialization, so we use the ASCII characters. So the first thing we know, 67 decodes to a C, and that's the first thing we learned. So the source text will appear following down this column. Then we read the next code word, which is 65, so that decodes to an A. So far, so good. And then the second step is add a new phrase to the dictionary. Right, so our Y now is A. We take the first character of Y, it's just A. And we take the previous phrase called X before, which is now just the letter C. And so the new thing we add to the dictionary is CA. All right, let's do one more. 78 is an N. So that's our Y. The first character is still N, it's just a single one. And we take the previous phrase that gives us AN, and we add this to the dictionary. Something to stress here, maybe if you implement this, you wouldn't really store these strings literally. Instead, you make note of the fact that this apart from the last letter, it's a phrase you had before. So you could just store it as one code word and then one new letter. So you don't need to store a long string in case you care about the space for the dictionary here. Okay, one more, and then things start slowly getting a bit interesting. So space, and we add after that previous phrase plus the new character to the dictionary. And one more time. And then for the first time, we see a code word used that was not just a single character, but was one of the ones that we added to the dictionary after that. So that's the input. We look it up. The new code starts here. So we find AN is one of the new entries in the dictionary. So we decode that. And now the first character of AN is A. That's our Y0. So we have to add the previous phrase followed by A into the dictionary. Okay? Can it ever happen that what we try to add to the dictionary here is already in the dictionary? Any ideas? Suppose it was possible. So what would happen if BA is already in the dictionary before? It cannot happen. Can someone tell me why? Should have prepared a Slido question for this one.
Setting up the tree to make sure that there's no prefix.
Yeah, you're getting at the right point. I mean, first of all, yes, the decoder can't really know. You have to look at the encoder. And the encoder made sure that you always take the longest match and then add one new character. And now we're replaying the same thing. So if this had been in the dictionary already, then there should have been a longer match before. When B was chosen as the code word by the encoder, it should have chosen BA instead. And the fact that it didn't means it wasn't there. Okay, so this looks like it's all going fine until we arrive at this funny situation. The new code word is 133, and you see this is not in the dictionary yet. So we're kind of stuck because we would like to know what 133 is, but it's the same time this is the time step where we would fill this cell. And this can happen because the encoder is always one step ahead of us. Remember, encoder does encode a new phrase and add a new thing to the dictionary. The decoder has to wait with the adding of the new thing to the dictionary until it has seen the next phrase. And so it can happen that because you wait, you need the same phrase right again. So it looks like this is a dead end. And the reason is this one step behind in creating of the dictionary. So putting this in a different way, we want to use a code that we're just building. And there's a very, very specific situation where this can happen. And luckily, we can analyze this situation and solve it because there's only one specific case where this can occur. So here's the situation, indeed the example from before if you followed it through, but try to not read ahead. So these three characters, Y, are not known to us yet. Okay, the decoder is at the stage, it knows X, that was the previous step. Maybe show this one more time. So we know XAN, that's the last thing we decoded. We are at can ban. And then comes this new part, can ban, that's where we are. And then we ask for a phrase that we're just about to fill. Now, when we create this phrase in the encoder, we of course know what this text is. And after we encoded Anna, we add the previous phrase and C. So this Anna here. And you notice it's the same string here. And that's not quite coincidental. Because if this thing that you use now, if you create a code word and then use it right away, that must mean that this X here is the same as this here. So the new phrase is the one you just inserted. So the new phrase Y is the same as XC. That's why I put it here below with these green bars indicating these are the same characters. Because the encoder creates a new phrase and then uses it right away. That means it must be the same thing he just inserted. And that also means we know what X and C is because they're copied over. And so in particular, we know that C is the first character of X in this case. And X we do know. That was the previous phrase. It's a little tricky, but the thing is, if you write down all you know, the only potential situation is that the new phrase that you're trying to decode is the one that was just inserted. And so because you know X, you know that the first character of X must be the unknown character C. Okay? So you can actually solve this by getting, in this case, just setting C manually as an exceptional case, and then using that as Y and inserting the phrase in the dictionary after that, like before. Okay, I thought I had the example completed. I guess after that, maybe do that first. So in this case, we decode this by using that X, the previous phrase, has as first character A, and that must be our C. So if we take X and then C, we get ANA. That's Anna. So we can put this both here for the source text, the decoded text, as well as here for the new phrase we want to add to the dictionary. Okay, it might look a bit magic. Spelled out in code, it looks like this. There's not much beyond what I showed you in the example. One thing that we didn't care about in the example is the data structures to represent the dictionary. In this case, the easiest, because you want to access the dictionary by index. You have a code word and you want to look up what that stands for. So we don't use a trie, but instead we just use an array. And the array stores for each code word, it stores what it stands for, which can either be a single character or another phrase followed by one single character. We keep X around for the last phrase. We keep Y around for the next thing to decode. K is whatever we would insert to the next free code word, so the next position in the dictionary that is not used yet. Initially, we set this like We initialize the dictionary with all the alphabet symbols, so the next free one is after that. And Q is the code word, so that's the next thing from the coded text. And then we go through all the letters in the coded text. The letters are numbers here. It's an array of code words. It's already split up the bits into code words. We remember what we had in Y before, remember that in X, then we take the next code word. And here, this is the special case. If the code word that we're trying to decode is the same as K, the next free one, then we're in this ANA special case. And in that case, we just set Y to X followed by the first character of X. In any other case, we said Y, we look up what the code word stands for, because then we have it in the dictionary. Then we append this to the output. Y is the decoded text. And then we have to store the new phrase XC as a new code word, and X we have remembered, and C is the first character of Y. And because we caught this special case here above, the adding things to dictionary is regular, is the same in both cases. Okay, there's one more line to finish this example off, but that is a regular case, so nothing special to say there. And so that completes that example. Now, before we discuss in more general a bit how well this works, time to wake you up with a slightly unrelated question to this decoding part. This is just about the encoding, if you want. Oh, is it? Thanks. I was wondering why you're so slow this morning. This is a fairly tough question. It means fully understanding the encoding part. And then analyzing it on the spot. So I'm asking for a bit here. Maybe this question is more for me as an excuse to talk about this best case than to really check your understanding. Quite a few more people on the live stream today, which is great that it's used. I wonder if that has any correlation with the nice weather outside, or if there are other things going on. I think I counted to something like 25 the people in live stream plus what we have here. So unless anyone's still busy thinking, let me show the answers first. And there's variety and an interesting peak for this one. The right one is root n. As I said, this is a fairly tricky one, but it's a great excuse to briefly look at this example. As often, well, I don't know. In this case, the single character repeated all over is a best case for compression. That's it's a feature shared by many compression methods, but maybe not all, so I won't promise more than I can. But in this case, it's about as good as it can go. So let's look at our text. And I'll just put a few A's here, and then we'll try to generalize from that. How would encoding work? For now, let's just look at the phrases that the text is split into. Remember, the encoding does this using a dictionary, but really what matters for this question is how many phrases do we get? And so this is just splitting the text up into certain subsegments. The first phrase is just the character A. We look up in the dictionary initially, it contains all the alphabet letters, there's nothing else in there. After that, we insert the previous phrase plus one more character. That's AA. And we find AA. So this is the next phrase. After we found that, we add this phrase plus a new A, which again we will use right away. So this is, if you want the text to practice this weird dead-end situation, this will be always in that case. It's always the phrase we just created that we now use again. And I guess you see the pattern now, right? We take 3 A's for the next one, then we add the fourth, then we use that right away, and so on and so forth. So what you get is something like, it's 1 plus 2 plus 3 plus 4. That is the number of characters we used so far. And what we want is, that's obviously the sum of the first integers. And we want to know, let's say, k phrases. We want to know that, and we want to have that this is at least n, because we need this to cover the entire text. And then you may know that this is very roughly, I can write this in precise notation. This is k squared over 2 as an asymptotic approximation. It's not exactly that, but pretty much. And so if you solve for k, that gives you square root n. It's an interesting little factoid to keep in mind. If you compare it with run length encoding, remember, best case for run length encoding, same text, compresses it down to log n bits, because you just tell the decoder how long the text is. In this case, you don't get log n, you get square root n. That's worse, but still pretty good. For many texts, you won't get that much of a compression. Okay, that as an order of magnitude maybe is useful to keep in mind. What else can we say about Lempel-Sif Welch? First of all, about the implementation, I presented it so that the output is a sequence of code words. You might want to further compress this because the code words probably don't occur equally, so they don't occur with equal frequency. So you might want to add another Huffman code after that, or some other code that can take advantage of this. Or you just write them in binary. Depends a bit. Then what I told you so far is it was a bit of a lie. I said we fix the size of the dictionary as 2 to the d, so that we have d bits for each code word. But if we keep encoding along a longer text, then we run out of space in the dictionary. So we need a rule to do what we do in this case. And there are different sensible options. We can add more bits to the code words to make room. We can also just say, forget the dictionary and start from scratch again. Or, well, scratch means we start from single alphabet symbols and then filling up again. Another option is to trigger this case even before the dictionary is full and have some heuristic that detects when maybe it's a good idea. Why would you maybe want to flush the dictionary earlier? The idea is there's some portions in the text that are similar, and then there's a different portion in the text that has different characteristics. And all of this compression method is using that things you've seen before occur again. And if that's no longer the case, then it's maybe a better idea to forget what you've seen and start again. But this is a gray, wishy-washy area a bit. There's no very clear rule when and how you should do this. So practical implementations like zip, they have some rules for this. Sometimes the dictionary size is a parameter you can specify if you don't just click the default option, but you use some tool that shows those. So often these are things you can play with and you can fine tune it. But for many applications, it doesn't matter too much. In terms of running time, they both can be implemented so that they run in linear time, which is the best you can hope for if you have to read the text. So that's pretty decent. So we like that they're fast. You can apply them in a streaming-like fashion if you have some rule for how the dictionaries are handled if they get full. You can do this in one go, right? It's not like Huffman that you have to scan the text first, count all letter frequencies, and then start coding. You can do this in one go, both encoding and decoding. And that's why this is also used as transport level compression. You can specify this as part of HTTP, that it compresses the payload. And so it has to work in this way. All right, also it achieves good compression for many types of data. You all have used zip, and unless you zip a zip file again, or zip something like an already compressed JPEG image or video, it usually works quite well and gives you some decent compression of, I don't know, 50%. Some downsides is if you have very, very long ranges of repetitions. So you have a huge text file which is copied twice, say as a hypothetical scenario. If that is too big for the dictionary to contain everything, it might get flushed and you don't recognize this repetition. That's inherent in this method in a sense, because you will run out of space for the dictionary eventually, or you will get some hit. If you increment D, you don't run out of space, but your code words get longer. That's also somehow wasteful. Yeah, so let me point out that the no-free lunch theorem that I promised you for last week is on this week's tutorial. It's always confusing because I'm thinking about the next tutorial that I'm putting up, not the one that you're already working on. So this is up on the website now, and you'll discuss this with Ben this week. So there's a nice little theorem that proves compression cannot always work. I mentioned this a couple of times. Yeah, but by and large, this is still a method of high practicality and is used in many places. And here's a quick overview of where the different compression methods that we've seen are used or where they're good for. And this summarizes just the summary slides of the previous section, so I don't want to go over this in more detail. It's kind of a service to you to not look it up on the other slides.